Hello everyone, welcome to part 2 of Unit 1 on Cloud Introduction and Cloud Infrastructure. In this section, we will be covering cloud delivery models and services, cloud deployment models, ethical issues and major challenges, and cloud infrastructures. Cloud computing services are mainly divided into three service models: IaaS, PaaS, and SaaS. That is, infrastructure as a service, platform as a service, and software as a service. The first is infrastructure as a service. In IaaS, the cloud provider offers basic infrastructure resources such as virtual machines, storage, and networking. The user manages the operating system and applications. Examples include Amazon Web Services EC2, Azure Virtual Machines, and Google Compute Engine. The next model is platform as a service. In PaaS, the provider offers a complete platform for application development and deployment. Developers can focus on coding without worrying about managing servers or infrastructure. Examples include Heroku, Google App Engine, and AWS Elastic Beanstalk. The final model is software as a service. In SaaS, software applications are directly provided to users through the internet. Users simply access the software using a web browser. The provider manages everything, including infrastructure, platform, and application maintenance. Examples include Google Workspace, Microsoft Office 365, and Salesforce. So the main difference is IaaS provides infrastructure, PaaS provides development platform, and SaaS provides ready-to-use software applications. This tag explains how responsibilities are divided into three cloud service models. The stack shown here includes different layers such as hardware, network, virtual machines, operating system, frameworks, and applications. In infrastructure as a service, the cloud provider manages the infrastructure part like hardware, networking, and virtualization, while the user is responsible for operating system, applications, and frameworks. In platform as a service, the provider manages even more layers, including operating system, runtime, and development platform. The user mainly focuses on developing and managing applications. In software as a service, almost everything is managed by the cloud provider. Users simply access and use the software through the internet. So as we move from IaaS to SaaS, the responsibility of the user decreases while the responsibility of the cloud provider increases. The examples shown here are Amazon EC2 for IaaS, Google App Engine and Windows Azure for PaaS, and Google Apps and Microsoft BPOS for SaaS. To understand IaaS, PaaS, and SaaS more easily, let us take a simple analogy of baking a cake. First, think about infrastructure as a service or IaaS. In this case, it is like renting a kitchen. The kitchen already has electricity, ovens, tables, and basic infrastructure. But you must bring your own ingredients, prepare the batter, bake the cake, and manage everything else yourself. Similarly, in the IaaS, the cloud provider gives infrastructure like server storage and networking, while the user manages the operating system, applications, and software. Next is platform as a service. Here, it is like entering a ready-to-use baking setup. The kitchen, ingredients, and baking tools are already arranged for you. You mainly focus on preparing and decorating the cake. Likewise, in PaaS, the cloud provider manages the infrastructure and platform, while developers focus mainly on the application development. Finally, software as a service. This is like directly buying a ready-made cake from a bakery. You simply use the final product without worrying about ingredients, baking, or kitchen setup. Similarly, in SaaS, users directly access software applications through the internet without managing infrastructures or platforms. So, in simple terms, IaaS gives the infrastructure, PaaS gives the ready development platform, and SaaS gives the complete software solution ready to use. Next, let us move on to cloud deployment models. Cloud deployment models define how cloud infrastructure is organized and who can access it. There are four major cloud deployment models: public cloud, private cloud, hybrid cloud, and community cloud. First is the public cloud. A public cloud is available to anyone over the internet. Services are shared among multiple users and managed by cloud providers like Amazon Web Services or Google Cloud. A simple analogy is a public bus. Anyone can use it by paying the required fare, and the transportation company manages the entire system. Similarly, public cloud resources are shared among many users. The next model is the private cloud. A private cloud is dedicated to a single organization. Only authorized users from that organization can access it. An analogy is a private car. Only the owner or selected people can use it, and it offers better control and privacy. Likewise, private clouds provide higher security and customization. The third model is the hybrid cloud. Hybrid cloud combines both public and private clouds. Organizations can use private cloud for sensitive data and public cloud for general workloads. A simple analogy is using both your own vehicle and public transport depending on the situation. Similarly, hybrid cloud allows flexibility between private and public environments. The final model is the community cloud. In this model, cloud infrastructure is shared among organizations with similar requirements. For example, educational institutions, research organizations, or government agencies. An analogy is a shared apartment used by a group with common interests and rules. So each deployment model differs based on ownership, accessibility, security, and resource sharing. Ethical issues and major challenges. Along with the advantages of cloud computing, there are also several ethical issues and major challenges that organizations must consider. The first ethical issue is data privacy. Cloud providers handle large amounts of sensitive user data, so protecting personal and confidential information from unauthorized access becomes very important. For example, if medical records or banking information stored in the cloud are accessed illegally, it can lead to serious privacy issues. The next issue is data ownership and control. Sometimes users may not have complete control over where and how their data is stored in the cloud. This creates questions about who actually owns and manages the data. For example, when moving data from one cloud provider to another, organizations may face difficulties in maintaining complete control over their information. Another important issue is transparency and accountability. Users may not always know how cloud providers manage security, backups, or data handling processes. If a security breach occurs, it may become difficult to clearly identify responsibility. So, organizations using cloud services must carefully evaluate privacy policies, security practices, and service agreements before adapting cloud technologies. Cloud computing also faces several major technical and operational challenges. The first challenge is security concerns. Since data is stored online and accessed through the internet, cloud systems are always exposed to risks such as cyber attacks, hacking, and data breaches. If an attacker gains unauthorized access to a cloud server, the data of multiple users may be affected. The next challenge is compliance and legal issues. Different countries follow different data protection laws and regulations. Organizations using cloud services must ensure that the cloud provider follows the required legal standards. For example, healthcare and banking organizations must comply with strict data privacy regulations. Another important challenge is service reliability and downtime. Cloud services must maintain continuously available. If a cloud provider experiences downtime, businesses' operations depending on the services may get interrupted. The final challenge mentioned here is vendor lock-in. Once an organization becomes dependent on one cloud provider, migrating to another provider may become difficult because of differences in technologies and architectures. So while computing offers many benefits, organizations must carefully manage the security, legal, reliability, and migration challenges. Next, moving on to cloud service providers. For this part, the primary reference book is Cloud Computing Theory and Practice by Dan C. Marinesu. In this chapter, we will study AWS, Google Cloud, and Microsoft Azure, along with the major services and infrastructure components. Cloud infrastructure. This topic introduces the three major cloud service providers: Amazon Web Services, Google Cloud, and Microsoft Azure. These companies provide cloud infrastructure and services that allow users and organizations to build applications, store data, deploy services, and scale resources without maintaining physical hardware. First, Amazon Web Services, commonly called AWS, is a cloud platform provided by Amazon. It offers a wide range of services such as EC2 for computing, S3 for storage, databases, networking, and machine learning services. AWS has data centers located in multiple regions around the world and is widely used by startups as well as large enterprises. Next is Google Cloud Platform. Google Cloud provides services related to computing, storage, databases, analytics, and machine learning. Google Cloud is especially known for its strong data analytics and AI capabilities. The third platform is Microsoft Azure. Azure provides services such as virtual machines, cloud storage, databases, and AI services. Azure integrates well with Microsoft technologies, making it popular among organizations already using Microsoft products. So, these cloud providers allow users to access computing resources on a pay as you go basis, providing flexibility, scalability, and cost effectiveness. Now let us begin with an introduction to Amazon Web Services, commonly known as AWS. AWS was introduced by Amazon Web Services in the year 2006 based on the infrastructure as a service. The main purpose of AWS was to build a powerful computing infrastructure to support Amazon's growing business operations. Over time, AWS expanded rapidly and became one of the world's leading cloud platforms. This slide also mentions the large growth scale of AWS. By 2012, more than 200 businesses were already using AWS services. By 2017, AWS generated over $10 million in annual revenue, showing its massive global adoption. One important service in AWS is Elastic Compute Cloud or EC2. EC2 allows users to launch virtual servers called instances under different operating systems. An instance is simply a virtual server created in the cloud. Users can choose the required region and availability zone where the instance should be deployed. This slide also mentions Elastic IP address. This is a static public IP address assigned to an EC2 instance from the available pool in the availability zone. So overall, AWS provides scalable cloud infrastructure and virtual computing resources that can be accessed on demand through the internet. AWS Management Console. Once users create AWS services, they need a way to access and manage them efficiently. For this purpose, AWS provides the AWS Management Console. The AWS Management Console is a web-based interface through which users can control different AWS services from a single place. Using EC2, applications running on different operating systems can be launched and managed easily. When multiple EC2 instances need to communicate with each other, AWS uses a service called SQS or Simple Queue Service, which allows message exchange between instances. AWS also provides different types of storage devices. For example, S3 is used for storing files and objects. SimpleDB provides database support, and EBS provides block level storage for EC2 instances. To monitor system performance and resource usage, AWS provides CloudWatch. Another important feature is auto-scaling, which automatically increases or decreases resources depending on the workload demand. AWS also provides virtual private cloud, which helps organizations securely connect their own infrastructure with AWS cloud resources. So overall, AWS offers a complete environment where users can manage computing, storage, networking, monitoring, and scaling services through a centralized console. Configuration of AWS services. In AWS, different cloud services must communicate efficiently with each other as well as with users accessing the cloud from outside. For this purpose, AWS uses a cloud interconnect that supports high-speed communication between compute servers and storage servers within an availability zone. Communication is also supported between different availability zones and external cloud users. This diagram also mentions Network Assist Translation or NAT. NAT is used to map external IP addresses to internal IP addresses within the cloud network. This helps improve security and efficient network management. Another important concept mentioned here is multi-tenancy. In multi-tenancy, multiple users or organizations share the same physical infrastructure while still maintaining isolation between their resources. This improves server utilization and reduces the operational cost. So AWS infrastructure is designed to provide high-speed communication, secure connectivity, efficient resource sharing, and cost optimization. Let us now look at some important AWS terminologies and services. The first service is Simple Storage Service, commonly called S3. S3 is a storage service used to store large amounts of data and objects in the cloud. It supports storage of files ranging from very small sizes up to several terabytes. The next service is Elastic Block Store. Elastic Block Store provides block level storage volumes that can be attached to EC2 instances. To applications, these storage volumes appear like physical hard disk. Another important service is SimpleDB. SimpleDB is a non-relational database service that allows developers to store and query data using web service requests. Then introduces Simple Queue Service or SQS. SQS is a message queue service that helps multiple EC2 instances coordinate their activities by sending and receiving messages. For monitoring cloud resources and application performance, AWS provides CloudWatch. CloudWatch collects and tracks performance metrics to improve resource utilization. Another important service is Virtual Private Cloud. Virtual Private Cloud creates a secure connection between an organization's existing infrastructure and AWS cloud resources using a virtual private network. Finally, autoscaling automatically increases or decreases EC2 instances depending on workload demand. This helps AWS efficiently utilize cloud elasticity and maintain application performance. Another important AWS service is Elastic Beanstalk. Elastic Beanstalk is a service that helps users easily deploy and manage applications in AWS without manually handling the underlying infrastructure. It works together with several AWS services such as EC2, S3, Elastic Load Balancer, Autoscaling, and CloudWatch. One important advantage of Elastic Beanstalk is that it automatically handles application development, capacity provisioning, load balancing, auto-scaling, and application monitoring. Resources are automatically scaled up or down depending on the application demand. The service also provides several management features. For example, users can deploy new application versions, roll back to previous versions, monitor application performance through CloudWatch, receive email notifications about application status, and access server log files without directly logging into servers. So, Elastic Beanstalk simplifies application deployment and management by automating many cloud operations. Let us now move to another major cloud platform, Microsoft Azure. Microsoft Azure is a cloud computing platform provided by Microsoft. Windows Azure mainly consists of three important components: compute, storage, and fabric controller. The compute component provides the environment required for running applications and processing tasks. The storage component provides scalable cloud storage for storing data and files. The Fabric controller is responsible for deploying, managing, and monitoring applications within Azure infrastructure. Another important service is SQL Azure, which is a cloud-based version of Microsoft SQL Server. Azure also provides Azure App Fabric, previously called .NET Services, which offers services for building cloud applications. It also mentions about content delivery network, which helps deliver content such as images, videos, web pages, and files more efficiently to users across different geographical locations. So Microsoft Azure provides computing, storage, networking, database, and application services through Microsoft's cloud infrastructure. Another major cloud platform is Google Clouds. Google Cloud provides cloud services mainly under software as a service and platform as a service. Google has one of the largest cloud infrastructures in the world. Around 2012, Google was estimated to use nearly 1.8 million servers, and the number continued to increase rapidly. Google also maintains billions of lines of code related to its cloud infrastructure and services. Many popular Google services such as Gmail, Google Drive, and Google Calendar store and manage their data using cloud data centers. Google Cloud is widely known for high performance infrastructure, scalability, data analytics, and machine learning capabilities. Because of this, many organizations use Google Cloud for application hosting, storage, AI, and large scale data processing. Google Cloud provides a large number of services for computing, storage, application deployment, and cloud management. The first service is App Engine. App Engine provides an environment for developing and running web or mobile applications directly on Google servers. Initially, it supported Python and later support for Java was also added. It uses Google Query Language, which has syntax similar to SQL for database operations. The next service is Compute Engine, commonly called CE. Compute Engine allows users to create virtual machines with resources customized according to application requirements. Users can choose configurations ranging from small instances to powerful systems with multiple virtual CPUs and large memory capacity. It also supports SSD storage, automatic scaling, and multiple operating systems such as Ubuntu, CentOS, Windows, and Red Hat. Another important service is Container Engine. Container Engine is used for managing Docker containers using Kubernetes. It automatically schedules and manages containers based on user requirements. Next comes Cloud Functions. Cloud Functions is a lightweight event-based service used to create single-purpose functions that respond automatically to cloud events. These functions are written in JavaScript and run in a Node.js environment. Google Cloud also provides Google Load Balancing. This service distributes workload across multiple servers to improve scalability and performance. For storage, Google provides cloud storage, which supports multi-region storage for applications such as video streaming, websites, and image hosting. Database services include Cloud SQL, which is a fully managed database service, Cloud Bigtable, a high-performance NoSQL database for large workloads, and Cloud Data Store, a scalable NoSQL database for web and mobile applications. So Google Cloud provides a complete set of services for application development, virtual machines, containers, storage, databases, and scalable cloud infrastructure. Cloud also provides several services for big data processing, networking, security, and machine learning. For big data applications, Google provides BigQuery. BigQuery is a fully managed data warehouse used for large-scale data analytics. Another important service is Cloud Data Flow, which supports both stream processing and broad batch processing of data pipelines. Cloud Data Proc is used for managing Hadoop and Spark services in the cloud. Google also provides Cloud Data Lab, which is used for large-scale data exploration, analysis, and visualization. For real-time messaging and data streaming, Google offers Cloud Web. Network functionality in Google Cloud is managed using Cloud Virtual Network. CVN allows users to connect resources securely and isolate them within a virtual private cloud environment. Google Cloud also provides cloud routers for routing network traffic, Cloud CDN for low latency content delivery, and Cloud DNS for scalable and reliable domain name services. For security, Google provides Cloud IAM or Identity and Access Management. IAM helps manage permissions and user access to cloud resources. Cloud KMS is used for encryption key management, while Cloud Security Scanner scans applications for common vulnerabilities. Google Cloud also includes several management tools under Stackdriver. These tools support monitoring, logging, debugging, diagnostics, and error reporting. Finally, Google Cloud provides machine learning services such as Cloud Machine Learning, Cloud Natural Language API, Cloud Speech API, and Cloud Vision API. These services help developers build AI-based applications for text analysis, speech recognition, and image understanding. Google App Engine provides two environments for deploying applications. The standard environment called AESTD and the flexible environment called AEFLX. An application can run in either one or both environments depending on the requirement. The standard environment is optimized for fast scaling, quick startup, and efficient resource usage. It is suitable for applications that need automatic scaling with minimal management. The flexible environment provides more flexibility and customization. It allows developers to use custom runtime environments and configure applications more freely. The table also summarizes pricing and service codes for App Engine in regions such as US and Europe. Pricing depends on factors such as resource usage, storage, memory, and application traffic. Service code thus define the limits for resource consumption and application usage within the cloud platform. So App Engine provides both a lightweight scalable environment and a flexible customizable environment for deploying cloud applications efficiently. Energy use and ecological impact of large-scale data centers. Cloud computing providers such as Amazon Web Services, Microsoft Azure, and Google Cloud invest heavily in building large-scale data centers. These data centers contain thousands of servers, storage systems, networking devices, and cooling equipment required to provide cloud services continuously. Operating these data centers consumes a huge amount of electricity. Power is required not only for running the servers but also for cooling and maintaining the infrastructure. As the number of data centers increases, overall energy consumption also increases significantly. This leads to ecological impact on the environment. Many data centers still depend on electricity generated from fossil fuels such as coal and gas. Burning these fuels releases greenhouse gases which contribute to pollution and climate change. Therefore, improving energy efficiency and developing environmentally sustainable data centers have become important goals in cloud computing. With this, we come to the end of part 2 of Unit 1. The remaining topics will be covered in part 3. Thank you.